Hello everyone. In this lecture 12, we discuss the Cayley Hamilton theorem, its statement and the proof, and example related to Cayley Hamilton theorem, how to verify the Cayley Hamilton theorem. Now, what is Cayley Hamilton theorem? The statement: the Cayley Hamilton theorem, every square matrix satisfy its own characteristic equation. That is, if for a square matrix A of order n, we can say the characteristic equation, that is a characteristic equation A minus lambda in, the determinant of that. If we expand this, we can write minus 1 ki power n lambda ki power n plus a1 lambda power n minus 1, a2 lambda power n minus 2, and so on an. So every matrix is satisfy its own characteristic equation. That is the statement of Cayley Hamilton theorem. So this matrix, this equation can be right because this is the equation. So we replace lambda by x ki power n, a1 x ki power n minus 1, a2 x ki power n minus 2 plus an is equal to 0. So this is what, this is the equation, or we can say this is a characteristic equation for the matrix A. Now is satisfy if we replace x by a. So what we get? We get a ki power n plus a1 a ki power n minus 1, a2 a ki power n minus 2 plus so on, plus a small an in is equal to 0. These small a1 a2 a3 an are the coefficients, and this capital A is what? Matrix. So we can say every square matrix satisfy its own characteristic equation. That is the statement of Cayley Hamilton theorem. If we replace that lambda by a, so it is equal to 0. Now we take the proof of Cayley Hamilton theorem. As we know the statement of the Cayley Hamilton theorem, every square matrix satisfies its own characteristic equation. So for the proof, we write the characteristic equation of matrix A, which is determinant of A minus lambda in is equal to 0. If we expand that characteristic equation, so we get minus 1 power n lambda power n plus a1 lambda power n minus 1 plus a2 lambda power n minus 2, and so on an. So we get such equation, that is the expansion of that characteristic equation. Now the element of adjoint of that matrix A minus lambda I, if we take the adjoint of that determinant of that adjoint of that matrix, so are a polynomial in the term of lambda of degree n minus 1 or less, because the cofactor of the element, that because adjoint is what, a cofactor matrix, are at most the degree n minus 1 in lambda. So therefore we can say adjoint of A minus lambda in can be written as a matrix polynomial in lambda. That is, we get an expansion, that is b naught lambda power n minus 1 plus b1 lambda power n minus 2, b2 lambda power n minus 3, and so on, bn minus 2 lambda, and the last one is constant. Here b0, b1, b2 are the matrices. These are the coefficients of the matrices of order n cross n. Now there is a very important property of matrices here we use, that is, if we multiply matrix with their adjoint, we get a determinant of that matrix into the identity matrix of same order. So in that, by the help of that property, in that property we replace that A by that A minus lambda in. So we can write A minus lambda in, we replace that, and on that A we replace A minus lambda in and determinant of A minus lambda in. Now we substitute the value of adjoint A minus lambda in and the determinant of A minus lambda in. So we take that is the equation 1, suppose, and this is the equation number 2. So we put adjoint of a minus lambda I by the equation 2, and that one is what is a characteristic equation. We substitute here by the help of equation 1. So equation 1 and 2 put in that equation, we say 3. So we get an expansion that is a minus lambda in, and here we put the equation 2 at 1, and here we put the equation 1 into in. Now we calculate, or we can say we equate the coefficient of like power of lambda on both sides. Now when we equate the coefficient like power lambda, so first we equate the coefficient of power lambda power n. Here when that element is multiplied with that second element of this first, so we get a power lambda power n, and the coefficient is what, b naught, with negative sign minus in. And on the right hand side we get a coefficient minus 1 power n in, and then we equate the coefficient of lambda power n minus 1. So when that element is multiplied with the a, so we get a coefficient a b naught, and this second element of that equation left hand side b1 lambda power n minus 1 is multiplied with the second element of that, that is lambda in. So we get again we get a lambda power n minus 1, and the coefficient of that is b1 lambda, oh sorry, b1 in, and on the right hand side we get a1 in and minus 1 power n. And similarly for lambda n minus 2, we get a coefficient when that element is multiplied with a, so we get a coefficient a b1, this one, and when that element, the third element lambda power n minus 3 is multiplied with the lambda in, so again we get a lambda power n minus 2, and the coefficient is what, b2 in with negative sign, and on the right hand side we get a2 in. And similarly we continue, and we get the coefficient of lambda and the coefficient of for the constant. Both sides, if we evaluate the constant, what we get when that b n minus 1 is multiplied with a, so we get a b n minus 1 on left hand side, and on the right hand side we get a n minus 1 power n in. Now that equation, that coefficients, we multiply these equations successively by e ki power n, e ki power n minus 1, k power n minus 2 in, and adding all the equation means this multiply by e ki power n both side, that multiply with e ki power n minus 1, this one e ki power n minus 2, and similar way that multiply with the constant in. Now when we add these all the equations left hand side and right hand side, what will happen, the left hand side become 0. How? If we multiply an on left hand side, we get minus in b naught a n, then plus we add the left hand side a n minus 1 multiply with that term, so we get a n minus 1 into a is a ki power n b naught minus in b1 a power n minus 1. And similarly when a power n minus 2 is multiplied on the left hand side, and we add, we write a power n minus 1 b1 minus a n minus 2 b2 in, and so on. And similarly on the left hand side, what we get minus 1 power n, we get and take a as a common, we write a power n plus a n minus 1 and into small a1 plus a2 small a2 and a to a power n minus 2 and so on. and in also take as a common. So we get what? That equation, because right left hand side is 0, that term will be cancelled with that term, and this one is cancelled with that term, and the similar manner all the terms are cancelled the left hand side, and we get an equation this. So here what we'll see, that equation, if this equation is 0, so we can say this part is also 0. So we can say a power n plus a1 small a1 a power n minus 1 plus a2 capital A n minus 2 and so on is equal to 0. See here, if you note that this is what, if I replace that capital A, which is the matrix, with lambda, so we get a characteristic equation, lambda power n plus a1 lambda power n minus 1 small a2 lambda power n minus 2 and so on. So we can say this is what, this is a characteristic equation of the matrix A, and if we replace that lambda with A, so we can say this is what, this is a, if we replace that lambda with capital A matrix, so we can say, we can prove that the every matrix satisfy its own characteristic equation. Now take an example. We have to verify the Cayley Hamilton theorem for the given matrix and hence also find the inverse. So first we verify the Cayley Hamilton theorem, and by the help of that theorem we find the inverse of that matrix. Now we have given a matrix of order 3 cross 3. So first we write what, the characteristic equation. And what is that? Determinant of A minus lambda I is equal to 0. Now we write the determinant, and what is that? We just subtract the lambda in the diagonal, minus 1, 2 minus lambda, that is minus 1, 1 minus 1, 2 minus lambda is equal to 0. On expanding that determinant, we get an equation. And what is that equation? We obtain equation lambda cube minus 6 lambda square plus 9 lambda minus 4 is equal to 0. I'm just simplify that equation and write here. Now we have to verify Cayley Hamilton theorem. And what is that theorem? Theorem statement is what? Every matrix satisfy its own characteristic equation. So we replace that lambda, with A. Means in that equation we replace lambda is equal to capital A. So we get A cube minus 6A square plus 9A minus 4I, because we write here I means the identity matrix, because the constant we have to write in the matrix equation, so we multiply that I. So now we have to verify this equation is satisfied or not, means left hand side is equal to, we get a right hand side. So we take the left hand side, and we find the A cube, A square and A, and put in that equation, and we have to check is equal to the 0 matrix or not. Now we have to verify that equation. So for that we take the left hand side of that equation, that is A cube 6 minus 6A square plus 9A minus 4I. So for that we have to find the A cube. You can easily find the A cube. First you find the A square, A into A, then you find A cube, that is A square into A. So which is I already find out, the A cube we get is 22 minus 21, 21 minus 21, 22 minus 21, 21 minus 21, 22. This is A cube. minus 6 time of a square, that is, which is already I have to find it, that is 6 minus 5, 5 minus 5, 6 minus 5, 5 minus 5, 6. Then plus 9. Then we write the matrix, and matrix is 2 minus 1, 1 minus 1, 2 minus 1, 1 minus 1, 2. Then minus 4, and write the identity matrix of order 3, because we have a matrix of order 3, 0, 0, 1, 0, 0, 0, 1. Now, then you add the equation. What you get? You get 22 minus 6 into 6, that is 36. Then plus 9 times of 2 is 18, and minus 4, that is the first element. And similarly the second element, that is minus 21 plus minus 6 into minus 5, we get plus 39 in minus 9, and minus 4 into 0, we get 0. And in similar way we find the third element, that one you can write. What you observe, that the first one become 22 plus 18, we get 40, and minus 40, we get 0. The second one is also 0, third one 0, and all the elements we obtain here 0. You can also verify that. So here what we noted, that this equation is satisfied, so we can say Cayley Hamilton theorem is verified. Cayley Hamilton theorem is verified because it satisfies its own characteristic equation, because that equation is generated by the characteristic equation. Now we have to find the A inverse. For that, if the theorem is verified, then we can find the A inverse. If theorem is not verified, we cannot find the A inverse. So when Cayley Hamilton theorem is verified, so we can find the inverse. How we write the equation? Take A as a common. So we write A square 6A plus 9I minus 4. A inverse is equal to 0. And this will implies that equation. Now take that term on the right hand side. So we write 4 A inverse is equal to A square 6A plus 9I, and A inverse is what now? 1 by 4 A square 6A plus 9I. Now you can easily find the A inverse because you already find the A square and you know the matrix. So we write here 1 by 4, then you just write the matrix A square. A square is what? We obtain 6 minus 5, 6 sorry, that is 5 minus 5, 6 minus 5, 5 minus 5, 6, then minus 6 times the matrix. What is the matrix? 2 minus 1, 1, minus 1, 2, minus 1, 1 minus 1, 2. And then plus 9, we write the identity matrix. Then we add all them. So we get A inverse is 1 by 4, and we get 6 minus 12 plus 9, we get 3, 1 minus 1, 1, 3, 1, minus 1, 1, 3. So in that way, we also find the A inverse by the help of Cayley Hamilton theorem. But you have to remember, first of all, we have to verify the Cayley Hamilton theorem. And after verify, if the theorem is verified, then we find the inverse. Okay, student, remaining topics covered in the next lecture.